Hi, in this module I will discuss torsion of circular shaft. The loading on the shaft is twisting moment. When two equal and opposite torques are applied at the ends of a shaft, it is said to be subjected to twisting moment. For example, this shaft is subjected to two equal and opposite torques, one this and another in a direction which is opposite to this in this manner. So this shaft is subjected to two torques, one this and one this at the ends, but in opposite direction. For example, if you consider this torque, then this torque is acting in the anti-clockwise direction as observed by the person standing here, and this torque is acting in the clockwise direction as observed by the person standing here. So we can say that the direction of this torque is in this direction and the direction of this torque is in this direction. Due to the applied twisting moment, internal resisting torque is set up in the shaft. To know about the internal resisting torque, make an imaginary cut in the shaft as shown by this red line that divides the shaft into two parts A and B. Let the twisting moment, that is the load on the shaft, be one torque in this direction and the another torque in this direction. To know about the internal torque, consider section A and section B. On section A, a load is acting like this, and on section B, a load torque is acting like this. To keep the part A in equilibrium, an internal resisting torque must be acting in this direction. Let us call this internal torque as T. Similarly, an internal torque must be acting on part B in direction opposite to the applied torque. So internal torque must be acting in this direction. So small t is the internal torque on this cross section and small t is the internal torque on this cross section. So when shafts are subjected to twisting moment, internal torques will be set up on each and every cross section on the shaft. When a shaft is subjected to twisting moment, it is said to be under a state of torsion. So torsion means that shaft is subjected to twisting moment. Now let us see what are the effects of twisting moment, that is torsion. The first effect of torsion is to set up shear stresses on any cross section of the shaft. The internal torque on a cross section is equivalent to distribution of shear stresses. We have seen that due to the applied twisting moment, internal torque will be set up on the shaft. So due to the applied twisting moment T, this is applied, and internal torque T will be set up on any cross section. This is the internal torque acting on this cross section. This is portion A of the shaft. This torque T is equivalent to the distribution of shear stresses on this shaded cross section. The distribution of shear stresses should be such that they must give a torque T on this cross section. So distribution can be shown like this, where the shear stresses are acting such that at all the points this shear stress will be giving some moment, that is internal torque T at this point, which will be equal to the force into distance r. Similarly, this shear stress will also be giving moment about this point, and the moment will be equal to this distance into the shear force acting at this point. So the distribution of shear stresses can be related to internal torque on that cross section. To relate the shear stresses with the internal torque, consider any cross section. The internal torque about the center of the cross section, that is point this, can be found by taking moment of the shear stresses at point O. Let the shear stress at any distance r be tau. Therefore, the shear force due to this shear stress on this small area dA at any distance r from the center is given by tau into dA. So this is the shear force which is giving a moment of force into distance at point O. So to find the total torque due to all the shear forces, that is this shear force, 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 that is shear forces acting on all the cross section, we integrate this with respect to dA on the entire area A. This will give us the moment that is acting by this shear stresses on this cross section, and this must come as the internal torque T. Therefore, we can write T as equal to integration over the entire area T into R into dA. Now we know that the area of circle is given by pi r square. Therefore, a differential area dA will be given as 2 pi r into dr. Therefore, we can write this as 2 pi r dr. This is dA. Now to integrate equation, we need the variation of shear stress with respect to radius. So once we have found the variation of shear stress with respect to radius, we will come back to this equation and then put the value of shear stress and find the internal torque. Now the notation of this shear stress is tau x theta, because when you consider this cross section, it can be seen that this outward normal of this cross section is x. So this area, that is this shaded area, is the xth area. So this shear stress is acting on the xth area, and this shear stress is acting in the circumferential direction, that is theta direction. Therefore, this shear stress is acting on the xth plane in theta direction. So its notation is tau x theta. Due to tau x theta, there is shear strain gamma x theta. This gamma x theta means that there is a change between two perpendicular lines x and theta. Now to find the relation between tau x theta and the gamma x theta, we can use Hooke's law. Assuming the material to be linearly elastic and isotropic, we can say that gamma x theta is equal to tau x theta divided by g. The second effect of torsion is the angular displacement of one cross section with respect to other cross section. That is, there is twisting of cross sections which is measured as angle of twist phi. Consider this shaft. Suppose this cross section is a fixed cross section. When a twisting moment T is applied like this, then all the cross sections will rotate by some angle. For example, this cross section has rotated by this angle, this cross section has rotated by this angle. But this fixed cross section, that is this cross section, will not rotate. It is fixed. So if you consider the radial line on the fixed cross section, then after the application of twisting moment T, this line which was initially in this direction will not rotate and will remain in this direction. But if you consider this cross section at the free end, then after the application of twisting moment, this line has now rotated to this line, that is point B has now moved to point B dash, because the cross section has twisted, and this cross section is shown here. This point A has moved to A dash because of the twisting of this cross section. So we can see that all the cross section will twist by some angle after the application of twisting moment, except the cross section which is fixed, that is this cross section. Therefore, we can say that there is an angular rotation of one cross section with respect to other. For example, this cross section at the free end has an angular displacement of say phi 1 with respect to fixed end, and this cross section has an angle of twist phi 2, that is angular displacement with respect to this cross section. And it can also be seen that the value of phi 1 is greater than phi 2. that is maximum twisting, will occur on the free cross section and the twisting on fixed cross section will be 0. So if you consider any cross section at a distance x, that is this cross section, then this cross section will twist with respect to this fixed cross section, and another cross section at just a distance dx from the previous cross section, that is this cross section, it will also twist with respect to this fixed cross section. Now the difference of twisting between cross section 1 and cross section 2 will be d phi, because the distance between them is only dx. So if this cross section has twisted by say phi 1 and this cross section has twisted by say phi 2, then this phi 2 minus phi 1 will be equal to d phi. That is, this change in twisting of cross section 1 and 2 will be small, because this cross section are near to each other, having a distance of only dx between them. Consider this differential part of the shaft of length dx. The relative angle of twist between these two cross section is this d phi, that is, this cross section has twisted by an amount d phi with respect to this cross section, and also point B has come to point B dash. Therefore this change in angle between x axis and the theta axis, which were initially perpendicular, is gamma x theta. Now if you consider triangle BCB dash, it can be written that BB dash is equal to gamma x theta into dx. And also if you consider the triangle B dash OB, that is triangle B dash OB, then from this triangle also BB dash can be written as R D phi. Therefore equating this BB dash and this BB dash, we get gamma x theta into dx is equal to R D phi. Therefore we get d phi by dx as equal to gamma x theta by r. Now we can derive the torsion equation for circular shaft. We have already learned that the internal torque T due to the applied twisting moment is given by tau x theta into r into 2 pi r dr, and this is dA. We have also learned that tau x theta is equal to gamma x theta into g. We have also learned that d phi by dx is equal to gamma x theta by r. So from these two equations we can say that tau x theta is equal to r d phi by dx into g. Putting this tau x theta here, we can write the internal torque T as integration over the entire area A r d phi by dx into g into r 2 pi r dr. So we can get this as integration g d phi by dx into 2 pi r cube dr, integration over the entire area A. Now this integration is with respect to dr, and this is the angle of twist phi. This angle of twist phi is a function of only x. As we have seen, this angle of twist was varying with respect to x. At the fixed end, that is x equal to 0, phi was 0, and on the free end phi was some phi 1. On this cross section phi will be some phi 2. So the angle of twist is varying with respect to x, and it is not varying with respect to r. Therefore, if phi is not varying with respect to r, then d phi by dx will also not vary with respect to r. Therefore, we can take this d phi by dx out of this integration, because this is constant with respect to r. Assuming the material to be homogeneous, g will also be constant. Therefore, we can write the torque T as T is equal to G taken out, d phi by dx taken out of the integration. We get integration 2 pi r cube dr, integrating over the entire area A. We can write this as G d phi by dx into r square into 2 pi r dr. Now this 2 pi r dr is actually dA. That is, if we consider this circular cross section, then at any distance r, we have a ring like this, then this differential area is given by 2 pi r into dr. So we can write T as equal to G d phi by dx into integration r square dA for the entire cross section A. Now this term r square into dA is the second moment of area, that is second moment of this area about the axis passing through point O. So we call this as G d phi by dx into dx as J. That is, J is the second moment of area about x-axis passing through point O. So we get T by J is equal to G into d phi by dx. But we have already learned that d phi by dx is gamma x theta by r. Therefore, we can write d phi by dx as gamma x theta by r, multiplying both sides by g. Now this g into gamma x theta is tau. Therefore, we can write tau x theta by r. So using this equation and the torque equation, we can write T by J is equal to tau x theta by r is equal to G into d phi by dx. This equation is called as torsion equation because it relates the torque T and the shear stresses that is set up on the cross section and the angle of twist that a cross section will have with respect to fixed end. For circular cross section, J about point O is given by pi d4 by 32. It is to be noted that this J is about x-axis passing through point O for this cross section. So let us see certain terms that we'll be using in this module. First is the polar section modulus ZP. It is the ratio of polar moment of area, that is J, to the radius of shaft. Therefore, this ZP is given by J divided by the radius of the shaft, which is capital R. So we can write this as pi d4 by 32 into d by 2. So this comes out as pi dq by 16. Torsional rigidity. It is the product of shear modulus and polar moment of area. Therefore, torsional rigidity is the G, that is shear modulus, into polar moment of area, which is J. So torsional rigidity is GJ. Torsional stiffness. It is the ratio of torsional rigidity to length of the shaft. So torsional rigidity per unit length is torsional stiffness. Now, while deriving the torsion equation, following assumptions have been taken. The material is linearly elastic because we have used Hooke's law. The material is homogeneous because while integrating we have taken G out of the integration. Cross sections remain circular after twisting moment is applied. So we are assuming that even after the twisting moment is applied, circular cross section has not changed in shape, it is still circular. Radial lines remain radial even after twisting moment is applied. We assume that before the twisting moment, the radial line OB was shifted to OB dash, but it is still remaining radial. Cross sections remain plane even after twisting moment is applied. That is, there is no warping of cross section. So we are assuming that cross sections that are plane before the application of twisting moment, if you see any cross section, this cross section, this cross section, all these are plane before the application of twisting moment, but we are assuming that even after the application of twisting moment, this plane cross section is remaining plane. That is, there is no warping of cross section. Warping is the axial movement of cross section when twisting moment is applied. When non-circular cross sections are subjected to twisting moment, cross sections undergo warping. For example, see this diagram. It can be seen that before the application of load, the plane section A, B, C, D has now warped, and the cross section after the application of twisting moment is A dash, B dash, C dash and D dash, and this A dash, B dash, C dash and D dash is no longer a plane. It is not a plane. So whenever non-circular cross sections are subjected to twisting moment, then those cross sections will undergo warping, but circular cross sections will not undergo warping. Before the twisting moment and after the twisting moment application, they will remain plane. Now let us draw the variation of shear stresses on the cross section of shaft. Consider solid shaft. We have seen that the equation of torsion is T by J is equal to tau x theta by R. So if we consider any cross section, for example this cross section, then let the twisting moment on this cross section be T, its polar moment of area be J. Therefore, we can write the variation of shear stresses on this cross section with respect to R as T by J into R. So it can be seen that on a cross section, shear stress tau x theta is varying linearly with R. So if we draw this variation, then shear stress tau x theta is 0 when R is 0. So at the center we do not have any shear stresses, and shear stresses are maximum when R is maximum. So at the end fibers we will have maximum shear stress, and in between the variation is linear. So we simply draw the variation like this. So at this point the variation will be this. At this point on the cross section, the shear stress will be 0. On this point of the cross section, the shear stress magnitude will be given by this value. So the tau max value can be given as T by J into R, that is capital R. So we can write this tau max as T by J divided by R. Now this J by R we know is equal to polar section modulus. So we get T by ZP. Therefore, the internal torque on any cross section is equal to the maximum shear stress on that section into the polar section modulus of that cross section. Hollow shaft. For hollow shaft, the cross section will be starting at some radius R1 and will be ending at some radius R2. Therefore, the value of shear stress is given by T by J is equal to tau by R. So tau x theta will be equal to T by J into R. Now in this case, J will be given as the J of only this portion because it is hollow up to radius R1. So it will be equal to pi by 32 d2 ki power 4 minus d1 power 4. So still the variation of shear stress is linear. So we can draw the variation. It will be maximum when R is maximum, and it will be having some value at this point, and the variation will be linear. But in the cross section from 0 to R1 there will be no stresses, that is stresses will be 0 because there is no material in this portion from 0 to R1. But beyond the radius R1 there will be shear stresses. So in this case tau max is given by T divided by J. J is pi by 32 into D2 4 minus D1 4 into R max. R max will be equal to R2. Now consider this shaft connected in series. Shafts are said to be connected in series when they have connections like this: shaft 1, shaft 2, shaft 3. Let these shafts we subject it to external twisting moment like this. This is some T1, and here at this end it is subjected to some external torque T2. Here it is subjected to some external torque T3, and here it is subjected to some external torque T4, and here it is subjected to some external torque T5. Now, to solve the questions of shaft in series, internal torque diagram is to be drawn. To draw the internal torque diagram, sign conventions are to be followed. So, the sign conventions are counterclockwise torque is to be taken as positive and clockwise torque is to be taken as negative. So let us draw the internal torque diagram for this shaft. Let this shaft is subjected to some torque T1 here, T2 here, T3 here, T4 here, and some T5 here. Let this length be L1, this length be L2, this length be some L3, and this length be some L4. To draw the internal torque diagram, draw a horizontal line. We can start either from left to right or from right to left. In this particular case, let us start from right to left. So we will be moving from here to here. Now stand at the end of this shaft to find the internal torque in this shaft. Look at the torque to the right of this line XX. This torque T1 is acting in the anti-clockwise direction. So we take T1 as positive because we have assumed anti-clockwise torques to be positive. So we mark T1 positive here. This is some T1. Now there is a change in loading at section XX. So mark another section just before the application of another torque, that is mark this new cross section XX, and see all the torques that are acting to the right of this cross section XX. The torques acting to the right of this cross section are T1 and T2. Since T1 is acting in the counterclockwise direction, therefore we take T1 as positive, and T2 is acting in the clockwise direction, therefore we take this as negative. Therefore we write T1 minus T2. So we draw T1 minus T2 as the internal torque in the portion L2 of the shaft. So we write this as T1 minus T2. So up till here the torque value is given as T1 minus T2. Now there is a new load acting at this point, which is T3. So make another section at this point, that is just before the application of new torque T5. Now to find the internal torque in the portion L3, look at all the internal loads acting to the right of cross section XX. The loads are T1 positive because it is acting in anti-clockwise direction, T2 negative because it is acting in clockwise direction, and T3 as positive because it is acting in the anti-clockwise direction. So we have this torque up till this point, and this value is T1 minus T2 plus T3. Now since there is a change in loading at cross section XX, that is a new torque T5 has come, so choose another cross section XX here, that is just before the application of new torque T4. The internal torque in the portion L4 can be written by considering all the external loads to the right of cross section XX, that is torque T1, which is positive because it is acting anti-clockwise, torque T2, which is negative because it is acting clockwise, torque T3 which is positive as it is acting counterclockwise, and torque T5 because it is acting in clockwise, it is to be taken as negative. So this is the internal torque on this cross section XX. So we have the value T1 minus T2 plus T3 minus T5. So it will be somewhere here. Therefore this value will be equal to T1 minus T2 plus T3 minus T5. So we have found the value of internal torque on all the portions of the shaft. For portion L1, the internal torque is T1. For portion L2, the internal torque is T1 minus T2. For portion L3, this is the internal torque. For portion L4, the internal torque is this. Now, once we know the value of internal torque, we can use the torsion equation. Remember that the torsion equation is T by J is equal to G into d phi by dx. Therefore, from here we can write d phi by dx as equal to T by Gj. Therefore, we can write d phi as equal to T by Gj into dx. Integrating it, suppose this is the shaft. Consider this portion x1 and this section x2. So when the section is x1, let the angle of twist on this shaft cross section will be phi 1, and at x2 the angle of twist is phi 2. Let the internal torque on this shaft portion be T. Therefore we can write phi 2 minus phi 1 as T by Gj into x2 minus x1. Let this x2 minus x1 be L. Therefore we can write phi 2 minus phi 1 as TL by Gj. So if we know the value of internal torque T on any portion, say L of the shaft, then we can write what is the angle of twist of cross section 2 with respect to cross section 1, that is phi 21 as TL by Gj. Therefore, to find the angle of twist for this case, assuming this as 1 and this as 2, suppose we want to find the value of 1 with respect to 2, then it can be written as, suppose this is 3, this is 4 and this is 5. Remember that a torque T1 was acting here and a torque T2 was acting here, a torque T3 was acting here, and a torque T4, and here a torque T5. So this phi 1 2 can be written as phi, that is angle of twist of 1 with respect to 3, plus angle of twist of 3 with respect to 4, plus angle of twist of 4 with respect to 5, plus angle of twist of 5 with respect to 2. Now this phi 1 3 can be written as torque in section 1 3 into length of 1 3. Length of 1 3 is L1. So this is TL1 by G1 into J1. Suppose the polar moment of area of this portion L1 is J1 and it is made up of some material G1. And similarly, phi 3 4 can be written as internal torque in 3 4 into length of 3 4. Length of 3 4 was L2, so it is L2 by G2 into J2. Suppose this is of material G2 and its polar moment of area be J2. Plus for phi 4 5 we can write the internal torque in the portion 4 5 into length of 4 5, which is some L3 divided by G3 into J3, plus internal torque in 5 2 into length of 5 2. Length of 5 2 is L4 by G4 into J4. Now we have already found the value of T13, T34, T45 and T52. For example, the value of T13, that is internal torque in the portion 1-3 is T1, and the internal torque in portion 3-4 was T1 minus T2 we have found here, as it can be seen. Internal torque in the portion 3, 4, that is this portion, is T1 minus T2 plus T3, and in the last portion it is T1 minus T2 plus T3 minus T5. So we have found all this internal torque using the internal torque diagram, and then using the equation that phi is equal to TL by GJ, we can find what will be the angle of twist of cross section 1, that is this cross section, with respect to cross section 2, that is this cross section. Now consider this indeterminate shaft. This shaft is indeterminate because the reactions from the wall 1 and the wall at 2 cannot be found by using equation of statics. That is, we need additional equations of geometrical compatibility. For example, let this shaft is subjected to some external twisting moment T like this. Due to the application of this external twisting moment T, the reactions will be coming at end A and at end B. To find the reactions at end A, assume that the reaction at end A be TA and at end B be TB. These reactions are the twisting reactions because the load is a twisting moment. Now, since this shaft is in equilibrium, therefore the net twisting moment on this shaft must be 0. So the net twisting moment is TA minus, because it is in clockwise direction, plus T plus TB is equal to 0. So now we have one equation but two variables TA and TB. Therefore, to find the reaction at end A and end B, we need one more equation. This equation will be the equation of geometrical compatibility. Now in this case, we see that since cross section A as well as cross section B are fixed, therefore the twisting moment of cross section B with respect to cross section A will be 0. So if we say this is C, we can say that phi of B with respect to C plus phi of C with respect to A must be 0. We have already learned that phi is given by TL by GJ. Let this length be L1 and this length be L2. So we have to find the internal torque T in portion BC and in portion AC. For this we have to draw internal torque diagram. To draw the internal torque diagram, we can start either from left to right or from right to left. In this case, I will go from left to right. On this cross section XX, the internal torque is given by the torque acting on the left of the cross section XX, because we are moving from left to right. Since this torque TA is in this direction, we take this as TA. Now since there is a new torque acting at point this, so we take another cross section here XX. The internal torque in the portion L1 will be given by TA minus T, because this T is acting in this direction. So we can write phi BC and phi CA. Phi BC plus phi CA was 0. So we can write this as torque in portion BC into length of portion BC by GJ BC plus torque in portion CA into length of portion CA by G of CA into J of CA is equal to 0. We have found the torque in portion BC. The torque in portion BC is TA minus T and its length is L1. So we put it here, TA minus T into length is L1 by GBC into JBC plus torque in portion TCA was found to be TA into length L2 divided by GCA into JCA as equal to 0. So now we have one more equation containing TA, and we have already used one equation of statics, that is this equation. So we have two equation, two variable. Using this we can find the reactions T and TB. So this torque reactions T and TB are found by using one more equation of geometrical compatibility. So these systems are indeterminate shaft systems. Now shafts in parallel. Shafts are said to be in parallel when we have one shaft like this and another like this. Suppose they are subjected to total torque T. Then out of this total torque T, some will be acting as a load on this cross section and some on this cross section. So out of total load T, some will be acting as T1 on the outer shaft and some acting as T2 on the inner shaft. Now if we consider this cross section, due to the application of twisting load T, this line OB will move to OB dash. So if we see the angle of twist, that is this angle, for this outer cross section it will be phi. But if we see the angle of twist for this inner cross section, that is A has moved to A dash, it is still this angle which is phi. So we can say that phi of the inner cross section will be equal to the phi of outer cross section if the shafts are in parallel. So we can say T1 into L1, both the shafts are having the same length, by G1 into J1 as equal to T2 into L2 by G2 into J2. Suppose this outer shaft is made up of material G1 and having the second moment of area as J1 about polar axis, and for inner shaft it is G2 and J2, and we have one more relation between T1 and T2. Using these two relations we can find T1 and T2. Comparison between hollow and solid shaft is the comparison of the power, that is which shaft can transfer more power, solid shaft or hollow shaft. The power transmission by a shaft P is given as T, that is torque transmitted by them, into omega. Now the first comparison is on the basis of same RPM, same material and same outer diameter. The torque resisted by solid shaft will be given as the polar section modulus of solid shaft into tau solid maximum. We have already seen that the internal torque resisted by any cross section is given as its polar section modulus into the maximum shear stress on that cross section. Similarly, the torque resisted by the hollow shaft will be the polar section modulus of that hollow cross section into the maximum shear stress that is coming on that hollow cross section. Now in this case we have same outer diameter of both the cross sections. Suppose this is D, then here also the outer diameter will be D. Let the inside diameter be small d. Now the Z of solid shaft can be written as pi d cube by 16. We have already seen this. And the Z of hollow shaft can be written as pi d4 minus small d4 divided by 16 into capital D. We have already seen this. So putting them in the equation of torque, we can write power as solid shaft is equal to torque was Z into tau max into N for solid, and power for hollow was Z of hollow into tau max of hollow into N. N is the RPM. Therefore for solid shaft we can write pi d cube by 16 into tau max solid into N, power of hollow as pi d4 minus d4 by 32 into d by 2 into tau max hollow into N. Now since RPM is same and also the material is same, therefore both the shafts will be having same maximum shear stress. So we can write power transmitted by solid by power transmitted by hollow as this pi and pi will cancel out and this will be 16. So 16 again will cancel out. We will get t cube by d4 minus small d4 by capital D as equal to d4 divided by d4 minus d4. This obviously will be greater than 1. Therefore, in this case, solid shaft will be transmitting more power as compared to hollow shaft. So, solid shaft will be preferred over hollow shaft. If we have same RPM and same material and same outer diameter. This ends this module. Thank you.